5,000 light-years from here, a dying star is breathing out a cloud of gas. And that cloud is the coldest natural place anyone has ever found. Colder than the empty space between the stars. Colder even than the faint afterglow left over from the birth of the universe. And yet it is not the coldest place we know. The coldest place in the entire universe is a machine, on a table, in a lab, here on Earth. To see how that is possible, you have to know what cold actually is. Temperature is motion. Everything around you is trembling. The atoms in this air, in your skin, in the walls, jittering back and forth, and the faster they jitter, the hotter a thing is. To cool something is really just to ask its atoms to slow down. And if you slow them and slow them and slow them further, there is a floor waiting at the very bottom. A point where all that trembling would stop completely. Perfect stillness. We call it absolute zero. Nature almost never gets close. Even the emptiest deep space is not truly cold. It hums at about 2.7 Kelvin, just under 3 degrees above that floor, gently warmed by the leftover heat of the Big Bang. A glow that fills all of space that nothing out there can hide from. For a long time, that afterglow was thought to set the coldest a natural thing could ever be. Then astronomers turned their instruments on the Boomerang Nebula. It measures about 1 Kelvin, 1 single degree above absolute zero, colder than the background glow of the cosmos itself. The only place in all of nature we have ever found that slips beneath it, and it manages that with a trick. The dying star at its heart is flinging gas outward in a vast, fast, ever-widening gale, and a gas that expands quickly enough cools as it spreads. It is the same reason the air rushing out of a can turns cold against your hand. The nebula is hauling heat away faster than the universe can pour it back in. A star, in the act of dying, running its own refrigerator out across the dark. That is the champion of the natural universe, and we beat it, not by a little, by a margin almost impossible to hold in your head. In laboratories here on Earth, physicists have learned to take a small cloud of atoms and strip away its motion on purpose. They hit it from every side with finely tuned lasers, each push nudging the atoms slower, like walking into a stiff breeze from every direction at once, until the whole cloud is barely stirring. Then magnetic fields cradle what is left and skim off the last, fastest, warmest atoms, the way you would blow the steam off the top of a coffee. And what remains is colder than anything nature has ever made. How much colder? The Boomerang Nebula sits around 1 Kelvin. These clouds reach billionths, even trillionths, of a single degree above absolute zero. Right now, as you listen, there is a device floating overhead aboard the International Space Station, a place called the Cold Atom Lab, where a tiny knot of atoms hangs at a temperature the wider universe has never once reached on its own. The coldest known spot in the universe is not out in the sky. It is something we built, which leaves the obvious question. If we can get that close, billionths of a degree, why not go all the way? Why not simply take the last step and touch zero? Because zero will not be touched. And this is the part that turns the whole story over. Getting colder is not like crossing a room toward a wall you will eventually reach. It is like having a distance again and again and again. Each time you chill your atoms nearer to the floor, the next sliver of cold costs more than the last. More effort, more energy carried away. And the closer you get, the steeper that price climbs without end. To reach absolute zero exactly, you would have to take an infinite number of these steps. Not a very large number, an infinite one. And this is not a shortcoming of our machines, it is written into the laws themselves. The third law of thermodynamics does not say that absolute zero is hard, it says it is unreachable, a floor no one is allowed to stand on. So sit with the shape of this. There is a temperature, one single exact temperature, that the entire universe in all its vastness and all its history is forbidden to reach. Not the core of the hottest star, not the most violent collision, not the coldest dying nebula 5,000 light-years away. None of them has ever arrived there, and none of them ever will. It is the one place the whole cosmos cannot go. And we, soft, warm, short-lived things on a small blue world, have crept closer to that forbidden edge than any star, any nebula, anything in the sky ever has. We did not find the coldest place in the universe. We made it. And then we stood a billionth of a degree away from a door the universe itself will never open. So the next time you feel the cold, real cold, the kind that aches in your fingers, remember that it has a bottom you can never quite reach, and that we have leaned further over that edge than the darkest, deepest reach of space. Next time we turn all the way around and ask the opposite question. Not how cold a thing can get, but how hot. The other end of everything, where matter itself comes apart. You carry the weight of stars. Look up.